Good morning and welcome back to our webinar series on the Australian Flexible Pavement Design Method. And in this final week, we'll look at the Mechanistic empirical design method, how we use that to calculate the thickness of pavement structures. So here's my contact details once again. And I think this webinar will run for about 45 minutes. Just a reminder to, again, please, if you've got any questions, click on the Q&A button, type in the slide number and with your question. Thanks. So again, this week we'll be talking about part 2 of the Austroads Guide to Pavement Technology, which covers the pavement structural design. And specifically this week, the final week, we'll look at the mechanistic design method. So in this presentation, I'd like to first off just give you an overview of the design method. Then the processes that we use, the steps in the design method differ according to whether we're looking at fatigue of bound materials or in terms of permanent deformation damage. That's in terms of rutting. So I'll run through the design steps for each of those distress types and show the differences. And finally, what I'd like to do is just to highlight to you some of the opportunities that there are for research in pavement engineering that we've touched on during the course of these 6 weeks. So I'll just run through some of the ideas I have about areas that might be of interest. So in general terms, this is a diagram just explaining the concept of a mechanistic empirical design process. We've talked about in previous weeks about a response to load model, where we calculate a critical parameter. In the Austroads case, it's a critical strain in a trial pavement. And from that critical strain, we calculate the allowable load repetitions of that strain. We do that with performance relationships that we've discussed in previous weeks, like the asphalt fatigue relationship or the cement and materials fatigue relationship or the subgrade strain value. And then we assess the damage due to the expected load repetitions, that's your design traffic, and we come up with a damage calculation where the expected number, small n, of load repetitions divided by the allowable. And we're trying to select a pavement composition such that the damage is less than 1. So that's the basic concept in this method. And in previous weeks, we've run through the response to load model that we use, this linear elastic model that we use in Austroads, that's related to the field performance through our performance relationships. So when you go about working out a pavement design, these are the steps that you undertake. First off, it's an iterative process where you select a trial configuration of pavement and you select the required project reliability level. For example, on a freeway pavement, you might know from experience that you'll need, say, 300mm thickness of asphalt on a working platform of a granular material. And so you might start with that as the trial pavement configuration, select a thickness of working platform based on your experience and the subgrade strength on that particular road. You would also consider the design traffic loading on this road and select a trial configuration for evaluation. For each of those pavement layers, you then need to do the elastic characterization of the materials, work out the design modulus of the pavement layers and the subgrade. And then you lead on to steps 3, 4, 5, and 6. And that's what I'm going to discuss now. these steps from this point onwards. We've covered steps 1 and 2 largely in previous weeks, how you reach, how you undertake those steps. So what I'm going to concentrate now on is the steps 3, 4, 5 and 6. So in the Ostrode's design system, there are 3 critical strains that are used to predict life. There's a tensile strain at the bottom of asphalt layers, which is used for predicting the allowable loading in terms of fatigue cracking. And in terms of cemented material, you also use the tensile strain at the bottom of the cemented layer to estimate the allowable loading in terms of fatigue cracking of the cemented material. And we use the vertical compressive strain on the top of the subgrade here to estimate the allowable loading in terms of deformation or rutting of the surface. So, as we've mentioned previously, there are a whole range of axle group loads and types on roads. We have, for example, single axle with dual tyres, tandem axle with dual tyres, triaxle groups. And for each of those, we need to estimate the strains under each axle group load and type. So here again is some of the common axle group types. A single axle with single tyres, and that's commonly a steer axle on a truck, for example. Another axle group with single tyres is a tandem steer, and that might be on, you see those on concrete delivery trucks, for example, a twin steer, that was commonly called. Then we have axle groups with dual tyres, and the most common is a single axle with dual tyres. You might also have a tandem axle, which might be a trailer axle, for example, on a truck, or another trailer axle type is a triaxle group. So they're the common axle group types. And the way we address the damage due to those different axle group types varies according to the stress type. So in the case of fatigue of bound materials, we calculate the damage due to each load on each axle group type and then sum the total damage. Whereas when we're looking at the deformation damage, we use a simplified approach where we calculate the allowable loading in equivalent standard axles, or ESAs, that we discussed last week. So let's now look at the design steps that we use when we're assessing the fatigue damage to bound materials such as asphalt and cemented materials. So in this case, when we come to step 3 and calculate the critical strains, we're calculating the critical strains under each axle load. And then in step 4, we calculate the allowable loadings of each axle load. And from that, we calculate the damage, knowing the number of repetitions of each axle group load. So in terms of, this is an example here of how you would calculate the critical strains due to an axle group load during the design period. So when we're doing these calculations, we need to know the loads on each axle group. And for each of those loads, we calculate a critical strain, and from that, the damage. So one of the first steps you need as a designer is to know the traffic load distribution, the loads that are going to be on your pavement on different axle group types. Then you know what strains you need to calculate. So we start this process by considering the axle groups with a single axle. This is the simplest case where we don't have interactions happening between axle groups, axles within a group. So there are two principal types of axle groups with single tyres, and that's the single axle with single tyres and a single axle with dual tyres. So there are two basic simplified groups with only one axle in the group. So for each of those axle groups, we first calculate the strain under a 53 kilonewton single axle with single tyres, and also the strains under an 80 kilonewton single axle with dual tyres. So there are two critical values that we calculate to start off with. And you can see the contact stress here for the contact areas are different for those two different configurations. So we start off by predicting those two strains in our trial pavement. So for example, when we're talking about a single axle with dual tyres at 80 kilonewtons that we've just calculated, this might be the strain that we've calculated in our trial pavement, 175 microstrain. The other strains for other loads are undertaken by linearly interpolating that value. So we assume that the pavement operates in a linear elastic way. If you halve the strain, if you halve the load on the axle group, you halve the strain. So no allowance is made for stress dependencies of materials like granular materials, for example, in this simplified approach. Pavements is assumed to be operating in a linear elastic manner. So from that one value of calculating the strain under a load of 80 kilonewtons, we can estimate the strains in the pavement of a range of axle group loads of that type. And from the calculated strains, we can then calculate the allowable load repetitions of each of those axle groups using our performance relationships that we've seen in previous weeks, where we input the strains that we've calculated and estimate the allowable loadings. So the more complex situation occurs when you have more than one axle in the group. And for example, we talked about earlier twin steers, for example, we've got two axles, tandem axles with dual tyres and triaxles. So for these axle groups where there's more than one axle, there is interactions between the axles in the group. These are the strain responses here of a trial pavement, different trial pavement configurations. And you can see the amount of interaction varies. This one, for example, might be for the tensile strains at the bottom of a thin asphalt surfacing, where there's very low interactions between the axles in the group in terms of the strain at the bottom of the thin asphalt layer. Whereas if you have a thick asphalt layer, at the bottom, the strain at the bottom of that, there's more interaction between the strains induced by the two axles. So that's what complicates things in terms of axle groups that have more than one axle. There's a question of whether and how to allow for the interaction between the axles in the group. Michael Moffat of ARRB undertook a PhD at Monash and evaluated this issue, and we looked at a range of different methods that could be adopted by Austrade. So if you'd like to further details of how this evaluation was done, I refer to Michael's thesis. From that thesis, Austrade decided to adopt a simple method, and it was a conservative method. It was to divide the axle group into single axles. It makes no allowance for the interaction between axles in the group. So the approach is you divide multiple axle into a series of isolated axles. Say for a tandem axle, you'd be looking at the strains under 2 isolated axles, and you predict the strains under those isolated axles, and you calculate the allowable loadings for each isolated axle with a formula like this, and then take account of the number of axles in the group to come up with the allowable loading of the axle group from the allowable loading of an individual axle, and considering the number of axles in that group. So this is an example for a tandem axle with dual tyres. So you divide the group axle load by 2, and then you estimate the individual isolated axle loads. And you then predict the strains under each of those isolated axles. And when you isolate those axles, they are single axles with dual tyres. So we've already calculated what the values are under single axles and dual tyres earlier. So for example, when there's an 80 kilonewton load on a tandem axle, that comprises 2 single axle with dual tyres at 40 kilonewtons. So this strain here is the strain under a 40 kilonewton single axle with dual tyres, but there are 2 repetitions of it. So the allowable loading allows for the number of repetitions in the group. And this is the formula here, say for fatigue, where this gives you the allowable loading of the isolated axle, and then you divide it by the number of axles in the group. In this case, there are 2. So you calculate the allowable loading under a single axle with dual tyres, then you divide it by 2 to get the allowable load repetitions of that axle group. So we do that same process for all axle group types. So you can see here, all we need for this process is just those same 2 calculated strains that we talked about earlier. A 50 kilonewton single axle, single tyre strain, from which we can calculate the strains under all sorts of single axles and single tyres. And also we can use those same strains to estimate the strains under a single axle, under a tandem axle with single tyres, by isolating the axles, in this case, into 2 individual axles. And the same for the tandem axle, for the other axle group types. We'd already talked about single axles with dual tyres, and this was the value that we calculated earlier for a single axle with dual tyres. We can then also estimate the values for the triaxle group by dividing the group load by 3, and these values then are single axle dual tyre loads at 1/3 the value of the group load. So for example, a 90 kilonewton triaxle group, this strain here is the value of a single axle under a load of 30 kilonewton. So having calculated the allowable load repetitions, and from our traffic load distribution, our traffic analysis that we discussed last week, we know the expected number, and we know how to calculate the expected number of repetitions of each group. So if we divide the expected by the allowable, we calculate the damage due to each load on each group, and then we sum the damage due of that group, and in this case it's 0.27 for the single axle with dual tyres, and then we consider the damage due to other axle group types and sum the overall damage due to the design traffic. And the objective is selecting a trial configuration such that the damage is less than 1. So if you calculate the damage as 1, this, for example, in this pavement configuration, the end result might have been acceptable, and and it wasn't necessary to undertake another design. But if the value exceeded 1, you might start the design process again, select another trial pavement configuration, and run through the calculations again. So you can see that it's an iterative process where you select a trial, assess the damage, and decide whether or not you need to look at another trial configuration. So please remember, send in your questions if you have some. So now I'll discuss the different approach that we use when we're assessing the permanent deformation damage. And this is a simplified approach compared with the approach that we use for looking at fatigue cracking damage. Last week we talked about the fact that when we express design traffic in the mechanistic design method, we use 2 approaches. And in the case of fatigue, we look at the cumulative number of axle group loads of different axle group types, as we've just discussed. But in the case of deformation damage or rutting damage, we use a simplified approach based on equivalent standard axles. And we discussed that last week. And the reason we do that is in the mechanistic design method, we use a simplified approach to calculating the allowable loading. We calculate the allowable loading of the pavement in equivalent standard axles. So that's why we calculate the design traffic in equivalent standard axles as well, the same unit. So in this case, the design steps vary from what we discussed earlier. When we get to step 3 and look at the critical strains, it is only under one axle, which is an 80 kilonewton standard axle, which is a single axle with dual tyres loaded to 80 kilonewtons. So that's our definition of a standard axle. And from that, we calculate the allowable loading in equivalent standard axles and compare that to the design traffic in equivalent standard axles. So in this case, there's only one critical strain that we need for the calculations. We don't need to calculate or estimate the strains under each axle group load of each axle group type, just a single value of strain under one load of one axle group. And the strain that, I'll just go back to this slide, the strain that we are estimating, again, is the vertical compressive strain on the top of subgrade. That's what we use to estimate the allowable loading in terms of surface rutting in the pavement. We've discussed that in previous weeks. So it's the allowable loading to surface rutting, at which stage the pavement would need to be rehabilitated. Now, as we discussed, I think it was last week, there was a question about what is that condition that we're designing for, specifically how much and rutting and what extent. And we don't specify that in the guide, but as I mentioned last week, my view is it's roughly 10 to 20% of the length with about 20 millimetres rut depths. So that's about the condition in which roads are rehabilitated. It does vary a bit with the importance of the road. Freeways, there might be a different intervention level than a rural highway, for example. So we don't specify in the guide, but the allowable loading is to a terminal condition when the pavement needs to be rehabilitated. And so we estimate that allowable loading from the vertical compressive strain on the top of the subgrade under a single axle with dual tyres loaded to 80 kilonewtons, our standard axle. So here's the standard axle configuration, 80 kilonewtons, 20 kilonewtons on each tyre. The contact stress that we use is 750 kPa. We have a set radius of the load, a circular load it's characterised as, and we're calculating the critical strains on the top of the subgrade, both between set of tyres and under the set of under one of the tyres, and you take the maximum of those two values and use that in the performance relationship. So having calculated the strains under this standard axle load, we then use our performance relationship to calculate the allowable loading before an unacceptable level of pavement surface deformation develops. So the units are equivalent standard axles. So having calculated the allowable loading in equivalent standard axles, we then need to calculate the design traffic in equivalent standard axles, as we talked about last week, and then the allowable and the design traffic will be compared, and if the allowable ESAs exceeds the design traffic, the pavement would be acceptable. Otherwise, you're back to step one and select another trial pavement configuration and start the process again until the allowable loading exceeds the design traffic in ESAs. So you can see this approach is a much simpler approach than estimating the damage under each axle group load of each axle group type. Okay, so finally, as I mentioned at the start, I'd just like to mention 4 key research opportunities that I see that are available for people to explore. These are the needs that I've touched on during the course of these 6 weeks. So I'll just summarise some of the key ones that I see anyway. So there's certainly a need to improve our ability to predict rutting of pavements. And we just discussed this in weeks 2 and 6. We have this subgrade strain relationship, which is used to estimate the surface deformation. But because it doesn't look at the rutting of individual pavement layers and subgrades, we're unable to optimise the use of materials with that relationship. We really need to have an ability to predict the deformation of individual materials, and then from that estimate the surface rutting. I've mentioned that we've started some work along those lines over the last 10 years. We've made some progress, but it still needs further development. And part of that also, as to develop that and take it further, we need improved methods of predicting moisture in pavements, particularly in relationship to the deformation of granular materials. We need a much better ability to be able to predict those so that we can then predict the deformation. In terms of taking the deformation of asphalt into account, we need processes to estimate pavement temperatures, and there has been some work along those lines, and I think we're well advanced in that respect. So a significant challenge remains is predicting the moisture content, the ability to be able to predict surface rutting. The next sort of major area is improved methods of predicting asphalt fatigue cracking. Fatigue cracking is the common distress type that limits the pavement or dictates the pavement thicknesses in a lot of our pavements. So it's a critical distress type that we design for. And in week 3, we discussed some of the characteristics we use in design. And I did touch on the fact that we use a fatigue relationship that was developed by Shell about 40 years ago, based on European mixes. And we desperately need an Australian laboratory fatigue relationship that reflects Australian mixes today. And from that, we also need to develop in-service fatigue relationships across a range of in-service temperatures. My view is that we don't, at the moment, predict the fatigue at elevated temperatures in the right way, and I think it's resulting in an over-design of pavements in the hotter areas of Australia. So, to me, that is a significant issue for Australia, to be able to predict the in-service performance of pavements in terms of fatigue at elevated temperatures in the northern parts of Australia. Another significant limitation for our prediction method is that we don't allow for the variation in moduli and fatigue characteristics with aging and loading. We use initial modulus values and initial fatigue characteristics to predict performance over 30 or 40 years. And we know that these characteristics change with time and with loading. And it would be beneficial to be moving to a method that recognises the changes in these properties with time rather than using single values. Another area that needs some further development is the elastic characterisation of granular materials and subgrades. And I talked a bit about that in week 2. And I gave you some idea of the work that we've been undertaken with non-linear finite element model to improve the ability to predict the modulus of granular materials and subgrade compared with our current linear elastic model. So we need to develop some pathways to shift from this linear system that we have to a non-linear stress-dependent characterisation of these materials. There's a need to develop methods to measure subgrade modulus. We don't have those values at the moment. I mentioned that in week 2 as well. Concerns about how you prepare specimens at the right moisture content for testing. We have a simplified approach for estimating subgrade modulus, and it has a major influence. Subgrade modulus has a major influence on designs, and we currently use this very simplified approach, 10 times the CBR. There are various empirical rules like this used throughout the world. There's a need to replace that and develop design a process for design moduli that reflects the stresses in trial that are applied to the subgrade in trial pavement configurations. We also use a lot of presumptive values for granular moduli rather than using measured values, and that is tied to the simplified linear elastic model we used. If we had a non-linear finite element model, we would be in a better position to move away from those, and to assist in that respect, we need to develop presumptive moduli stress dependencies for granular materials and subgrades. So I touched on this a bit earlier. The fact that we don't allow for the variation in material properties with time and loading, and we use single values of modulus, for example, and no allowance for the variation with fatigue with time. And we could investigate and research incremental recursive models to calculate the damage in each month of the design period and allow for the change in properties with time. So there's some of the opportunities I see for further research and some of the challenges ahead. So please, if you have any questions, please send them in. And we'll move now to the questions.
Thank you, Jeff. We have one question from the audience. The interaction between axials, I think the slide number is not mentioned. So as thickness of the pavement increases, the interaction between axials will increase significantly. So how does it take into account in the pavement design?
Right. As I mentioned when I was going through here, this low interaction here might be for a thin asphalt surface, but where we're looking at the strain at the bottom of the thin asphalt layer. So in that case, the axles essentially are independent of each other. There's no interaction. Whereas for a thick asphalt, there's interaction between the effect on the strain due to each of the axles in the group. And that effectively reduces the peak strains. That interaction reduces the peak strains that develop, tensile strains at the bottom of the asphalt. So in the Ostrodes method, we decided that a simplified and conservative approach would be to neglect the fact that this interaction actually reduces the peak strains and just use the isolated axle values rather than the reduced values that result from the interaction. So that was addressed in, as I mentioned, in Michael's thesis. He looked at various options and we ended up saying we'll adopt a simple method and also a more conservative approach by looking at the strains under isolated axles rather than allowing for the interactions between the axles in the group.
Thank you for the clarification, Jeff. That's the only question we received from the audience.
Okay.
So, on behalf of the SPARC Hub Executive Committee and the Management Committee, so I think, sorry, Jeff, you want to continue?
No, I was just going to close off myself. So I welcome some comments from you.
Okay, yeah. So, yes. So we would like to thank Dr. Jeff for taking effort in preparing and delivering this series of webinar lectures for SPARC Hub researchers during these unprecedented times. And the webinar was very useful for our research activities undertaken at present. And thank you very much.
Well, thank you for the opportunity and for your interest in learning about Australian flexible pavement design. And looking forward to catching up with you all at SPARC soon. So thank you again.
Thank you very much, Jeff.